Okay, so let us review what I did. We try to solve this equation, y double prime plus y equal to 0. And as we stated, it is a trivial example because the solutions, two solutions, are very well known. The equation is an equation with constant coefficients, and the general solution is very well known, which is in fact c1 cosine x plus c2 sine x. Good. But for a moment, okay, we forget about this very well known solution and try to find a series representation of the two solutions. We choose x0, 0. Yes, as you see, each point is an ordinary point. Therefore, for simplicity, let us choose x0, 0. So we propose a series solution, power series solution about 0 of this form. Taking the second derivative and substitute into the equation, we arrive at this form. And therefore, to equate this series of ascending powers of x, 0 for all x, we have to equate the coefficients of like power of x to 0. So equating the coefficients of x to power n to 0, we get this equation. M plus 1, n plus 2, a n plus 2 plus a n must be 0 for all n. 0, 1, so on. Okay? Look, as you see, this is the coefficient of x to power n in the expansion. Good? So here, or solving for a n plus 2, we get minus a n over m plus 1, m plus 2. Yes, where we introduce a terminology and we say that this is a recurrence relation or a recursion relation terminology. So the equation, in fact, there are infinitely many equations, is called the equation for a n is called a recursion relation or a recurrence equation. Okay? So, as you understand, in the proposed solution, a n x to power n, it seems that there are infinitely many unknown coefficients. Yes? a0, a1, a2, a3, and so on are all unknowns. And we have infinitely many equations in infinitely many unknowns a n. Good? So let us solve the recurrence equation. Now, solving recurrence equation. So as you understand, the solution of the differential equation has been reduced to solving the recursion relation for a n to find the coefficient functions in the proposed series solution. Solving the recurrence or recursion relation. Let's write it again. A n plus 2 is minus a n over n plus 1, n plus 2 for n, 0, 1, and so on. So starting with n equal to 0, yes, solving step by step recursively for n equal to 0 first. We have a2 minus a0 over 1 times 2. Good. Which seems that we have minus 1 to power 1 over 2 factorial a0. Good. Let's solve the recursion relation for n equal to 1 to get a3 minus a1 over 2 times 3. Good. Which is again in that form 3 factorial a1. Now for n equal to 2, a4 is written as minus a2 over 3 times 4. But a2 has been determined from the previous step. So multiplying a2 by minus 1 and dividing by 3 times 4, we get minus 1 squared. Good. 2 factorial times 3, 4 gives 4 factorial a0. As for n equal to 3, we have a5 from this equation, which is a3 over 4 times 5. Similarly, a3 is known in terms of a1. So we get minus 1 squared. Substitution of a3 in terms of a1 here. We have 3 factorial 4 times 5, so 5 factorial, giving 5 factorial a1. Okay? And if we continue in this way, we see the structure of the coefficients. So in this example, it is not difficult to find the general term as a simple, nice formula. That is, I express a2 and look, it seems that the coefficients with an even index are all expressible in terms of a0, okay? And the coefficients with an odd index are all expressible in terms of a1, okay? So it is not difficult to prove by induction that a2k becomes minus 1 to power k over k factorial. Sorry, 2k factorial. Good, times a0. You can prove this by induction. And the coefficients with an odd index, say a 2k plus 1. Good. Seems to be minus 1 to power k over 2k plus 1 factorial a1. Good. So as you see, this relation is true for k, 0, 1, 2, and so on. And similar, this expression for a 2k plus 1, okay, have the index starting from 0. Now, we have to write down the solution. Now, we determine the coefficients in the proposed series solution, but we get different formulas corresponding to even index term and odd index term respectively. Therefore, writing the equation accordingly, splitting the solution or power series solution into two series containing even and odd index terms. Okay? So look, now splitting the power series solution into two series containing even and odd powers of x, okay, is we have, look, actually, our series solution we propose a n x2 power n may be written in that form. A 2k x2 power 2k. Look, which contains even indexed terms, or which contains the terms with even, proportional to even powers of x, like a0, then a2x squared, then a4x4. So even terms or even powers of x are all contained in the first series, and the terms containing odd powers of x have this. Therefore, a power series containing all powers of x may always be divided into two series containing only even powers of x and odd powers of x, respectively. Okay? Here, the reason to split the series into two series is that we get a formula for a2k and another formula for a2k plus 1. So, if you remember the formulas we get for a2k, we have a0 from 0 to infinity. So a0 times minus 1 to power k over 2k factorial is the formula, nice formula we get for a2k. So x2 power 2k plus a1, okay, from 0 to infinity. A2k plus 1 is written as minus 1 to power k, 2k plus 1 factorial, x2 power 2k plus 1. Good. So we nicely write down the solutions as a combination of two power series. Good. Where a0 and a1 remains arbitrary. Which is in a good agreement with the theory which suggests that such a second order ODE should contain two arbitrary constants in its solution. Good. So in this case, look, a0 and a1 remains arbitrary, and they are, in fact, where, look, so clearly a0 is nothing but y of 0, and a1 is y prime 0. Good. Actually, look, if you think that this is the series under consideration, actually from y of x written explicitly, a0, a1x, a2x squared, and so on. Look, y of 0 is a0. Put x equal to 0. We understand that a0 is nothing but y of 0. And similarly, from y prime, a1 plus 2a2x, and so on. So every term except the first one becomes 0 when x is 0. So y prime 0 is a1. Okay. So if we had an initial value problem, okay, where y of 0 and y prime 0 are both given, so or specified, then we determine a0 and a1 in this general solution. So this is the general solution, as we see, which is and y of x, the solution, or y of x, okay, stands for the general solution. Which is of that form. Look, a0, say arbitrary constant, a1 is another arbitrary constant. Good. So general solution is the combination of two independent solutions. Therefore, here we find that, we observe that this is y1 of x, the first solution in its series representation, or the series representation of the first solution has been obtained. Similarly, look, this may be identified as the series representation of the second solution. Okay? And it is obviously true that we recognize this series as the Maclaurin series for cosine x. And the second one is very well known. It is the Maclaurin series of sine x. So we obtain the very well known solution, which is the combination of cosine x and sine x. Okay? Now, you may say that this is a trivial example. Therefore, everything goes in a straightforward manner and we get the solution. But there is nothing which is altered if you consider a more general equation. The procedure of constructing a power series solution remains completely unchanged for any equation, provided that we try to expand the solution about an ordinary point. Okay? Now, if you want, let us review our power series solutions and then continue review of power series solution about an ordinary point. Here is a review. So look, first, let x0 be an ordinary point. Okay? Ordinary point of this equation, px y double prime, qx y prime, rx y, which is in general an equation with variable coefficient, or writing in the reduced form, a1x y prime, a2xy is 0. Okay? So what do we mean by saying that x0 is an ordinary point? Remember the definition of an ordinary point? We mean that both a1 and a2 are analytic at x0. So x0 is, this number is an ordinary point Okay? Means that both, okay, if both A1 and A2 are analytic functions at x. That is, they have a power series expansions about x0, convergent power series expansion. And recall, now we use the two theorems. Theorem 1 tells us that if A1 and A2 are both analytic at x equal to x0, so implying that x0 is an ordinary point, okay, then all solutions of our ODE, which is a second order homogeneous ODE with constant coefficients, are also analytic, okay, at x0. In fact, we say that they are analytic in some interval containing x0, are also analytic at some open x interval containing x0, okay? So in practice, all solutions of our ODE are also analytic in some open x interval containing x0. So in practice, this theorem tells us that in practice we may propose a power series solution about x equal to x0 of the form an x minus x0 from 0 to infinity, okay, which is convergent in some x interval centered at x0 with radius rho, and there is a non-zero radius of convergence. Geometrically speaking, this is an open x interval around x0. Okay. X0 minus rho. So it tells us that this power series solution we propose, okay, is convergent at any x lying in this x interval. Good? Now, about x equal to x0, to establish, in fact, we may propose a solution of this form, and we establish both two solutions, linearly independent solutions, in terms of power series, right? To establish both two independent solutions in power series form, or in the form of power series. Good. This is our first theorem. And now the most important property of a power series is that it makes sense if it is convergent. Therefore, it is important to find the radius of convergence. Of course, you can find the radius of convergence when you establish the power series solution, substituting the power series into the differential equation and finding the recurrence relation and solving the recurrence relation for an, you get a power series. So you can use any test known for calculus to find the radius of convergence. But in a differential equation course, this is unnecessary. And there is another theorem which tells us that the radius of convergence of a power series solutions is determined completely by the singular points of the differential equation. Okay? To be specific, let Z0 be a singular point. Please be careful. As we discussed in the previous lecture, complex singular points also play roles in finding the radius of convergence of a power series solution. So let Z0 be a singular point, maybe complex, or let's say real or complex, be a singular point which is nearest to x0. That is, the differential equation may have more than one singular point. What is important? We have to consider the singular point which is closer, or which is the closest to the x0, to the point at x0. Okay? So let D be the distance between x0 and z0. Good? That is z0 minus x0, the distance, okay, which is the okay, so considering two, in general, two complex numbers. So the modulus of this complex number gives us the distance between z0 and x0. Now, then this theorem tells us that rho, that is the radius of convergence of the power series solution we propose, is at least D. Okay, very nice. which means that when you consider the x interval centered at x0, we have this, and rho is at least d. Okay? In general, it is d, but sometimes rho may be larger than d. Some cases, the series solution may be reduced to a polynomial. Okay? The terms or the coefficients beyond some index are all zero, reducing the series to a polynomial. In that cases, it is convergent for all x. Okay. Anyway, so clearly, another important result from this theorem is that if there is no singular point of the ODE, then there is no bound for rho, then rho becomes infinity. Okay? So in which case we get that here is x0, here is rho, but okay, there is no singularity to give a bound, so rho goes to infinity. Okay, so a power series solution in that case converges for all x. Okay, so let us consider now a non-trivial example. Here is a non-trivial example. Find power series solutions of this equation, y double prime plus x, y prime plus y equal to 0. Okay? As you see, this is an equation with variable coefficients. So in general, there is no technique to find both two linearly independent solutions in closed explicit form. Okay? But the general theory tells us that we have to find two linearly independent solutions because the equation is second order. Now, is there any singularity? Look, the coefficients are 1, x, and 1. They are both analytic everywhere. Okay? So coefficients are one, x, and 1 are analytic everywhere. And none of them are undefined. Okay? At some real x. So there is no singular point. In other words, every point is an ordinary point. So let's choose x0, 0 for simplicity. It is an ordinary point. So now when we choose x0, 0, this means that we are interested in a power series in the form of a Maclaurin series. Right? So propose a solution, a power series solution of the form. Good? So what about, so x rho, where rho is infinity because there is no singular point. Okay, so all we need is to determine the coefficients, as in the previous example. Now, y prime substitution of y prime, which is this, from 1 up to infinity, n x to the power n minus 1, and y double prime, good, n minus 1, n x to the power n minus 2, starting from 2. These are mechanical calculation. We take derivatives of the proposed power series term by term. Good. And this series may be started from 1 because the first constant term has 0 derivative. And first term and second term, which are linear in x, okay, have second derivative, which are both 0. So this series may be started from 2. So substitution of y prime, and y double prime into the ODE. What is our ODE? It is this, y double prime plus x y prime plus y. So we have n minus 1, n x to the power n minus 2. This is the second derivative, times x times y prime. Good. So x times y prime becomes this, n x to the power n. Look, we multiply y prime by x. So xn minus 1 rises to n, x to the power n, plus y. So y is n x to the power n. Good. So we have to rearrange this series. And there is nothing to do with the second and third series. You can put them under one sigma sign. Okay. You can write the two of them. Look, actually, this series starts from 1 because the first term, when n is 0, is 0. So without any trouble, you may also start it from 0. Good, if you want. Because when you start at 0, you add 0, which doesn't change the value of the sum. Adding 0 to a sum doesn't change the actual value of the sum. So the two series here are all related to x to the power n. So they may be collected under one series, n plus an proportional to xn. Good. And this series can always be transformed into a series containing x to the power n by using this transformation. in place of n, I'm going to write n plus 2 in practice. Good. So the series will start from 0 because n increased to n plus 2. So n starts from 0 to infinity, n plus 1, n plus 2. In place of n, I write n plus 1, n plus 2, sorry, and x2 power n. Good. Which must be 0. So we can now express everything as a single series starting from 0 up to infinity, which is n plus 1, n plus 2, n plus 2, plus n plus 1, an, x2 power n, which should be 0 for all x. Good. So substitution of the series into the differential equation, we get this series, okay, in ascending powers of x. Good. First a constant, then x squared, and so on. So equating the coefficients of x2 power n to 0, what you get, so equating the coefficients of x2 power n to 0, we get the so-called recurrence relation. We obtain the recurrence relation, which is n plus 1, n plus 2, n plus 2. So this is the coefficient of x2 power n, coefficient of x2 power n, plus n plus 1 an must be 0 for all n, right? So we have to solve the recurrence relation to find the coefficients in the proposed power series solution. And we know that the resulting series will be convergent for all x. Good. So all we need, let's write the recurrence equation once again. Recurrence relation. Maybe written in that form, a n plus 2 is minus a n. So n plus 1 cancel each other out. A n over n plus 2 for all n, 0, 1, and so on. So starting again to solve this relation step by step for n equal to 0 first. So we have a2, which is a0 over 2. Good. And for n equal to 1, we have a3, which is minus a1 over 3. Good. Continuing in the same way, n equal to 2, we have a4, which is minus a2 over 4. Good. When n is 2, we have a2 over 4 with a minus sign. But a2 is known in terms of a1. So writing that, we get minus 1 squared over 2 squared a0. Good. It seems that the coefficient has that form. Okay. Then when n is 3, we find a5 from the recurrence equation, which is minus a3 over 5. So A3 is known in terms of A1, 0, 1, 2, 3, A5, A3, good. So we have minus 1 squared over 3 times 5A1. Good? A5 is written like that, but I think there is a mistake here. So when A2 is this, so this is not 2 squared, but it is 2 times or 4 times 2. Okay, so 3 times 5. Let's continue in this way. N equal to 3, so 4, sorry. We have A6, which is minus A4 over 6. So multiplying A4 by minus 1 and divide by 6, multiplying by minus 1, we have minus 1 cube, and 2 times 4, let's write it as 2 times 4. So 2 times 4 times 6. So it seems that we have the product of even numbers up to 6. 6 is the coefficient of A, or is the index of A. And for n equal to 5, A7 is minus A5 over 7. And A7 is known, and it seems that this is minus 1 cube times 3, 5, 7, A1. So again, the calculation, first few calculation of the coefficients, okay? Calculation of the first few coefficients show immediately that the coefficients with an even index are all proportional to A0. Okay, do not forget A0. And the coefficients of with an odd index like A3, A5, A7 are all proportional to A1. Okay? And a nice structure, again, a nice structure is observed. What is this, in fact? Look, A6 may be written as, look, there are 3 factors in A6. So each factor contains one product 2, because they are all even. So we have minus 1 cube over 2 cube times 1, 2, and 3 A0. Okay? I mean, I write 2 as 1 plus 2, 4 as 2 plus 2, and 6 as 2 plus 3. So we have 2 to power 3 times 1 times 2 times 3. Or it seems that A6 is written as minus 1 cube over 2 cube times 3 factorial A0. So if you look at this coefficient A4, it has the same structure. Good. This can be written as minus 1 squared. So this is 2, 1 times 2. So 2 squared, 1 times 2 is 2 factorial A0. Good. So the same structure. Therefore, continuing in this way, we see that the coefficients with an even index, okay, say 2k, has this structure. Minus 1, or even it is possible to incorporate this term, minus 1 over 2 cube over a0 over 3 factorial. Okay? So minus 1 over 2 to power k, a0 over k factorial for k, 0, 1, and so on. Good? So very nice again. So for this example, again, we find a very good formula for the coefficients in the proposed power series solution with an even index. Good? Similarly, if you look at the coefficients in with an odd index, you will see that, look at that. For example, look at A7. Is it possible to multiply throughout by 2, 4, 6 and divide by 2, 4, 6 to get this 2, 3, 4, these are terms, 5, 6, 7. So we multiply by the denominator by 2 times 4 times 6 and divide by 2 times 4 times 6. So minus 1 cube a1. So in this case, we see that, and here 2, 4, 6 is clearly 2 cube times 1, 2, 3, isn't it? Each factor contains a factor, 2. So totally we have 3 factors, 2, 2 to power cube, 1 times 2, and that. And the denominator is 7 factorial now. Okay? And this is 3 factorial minus 1 cube a1. This is a7. Good? Or you can think that a7 may be written as a6 plus 1 or 2 times 3 plus 1, and it is minus 1 over just minus 1 minus 2 times 3. Okay, this one, this index, minus 2 times 3, and 3 factorial over 7 factorial, and 7 is 2 times 3 plus 1 factorial. Good? A1. So from this structure, we can easily guess that a coefficient with an odd index like a2k plus 1. So here, this is just the case when k is 3. Okay? So for any integer k, it seems that the coefficients have the form minus 2 to power k, k factorial over 2k plus 1 factorial times a1. Okay? So we get also a nice formula for the coefficients with an odd index. This can be proved by induction. So because of this reason, we again split the power series solution into 2 parts containing even and odd terms separately. So again, writing the solution as that. So here is a 2k plus 1 and a 2k and a 2k plus 1 has the form minus 2 to power k, k factorial 2k plus 1 factorial a1. Okay? So splitting this series solution into two parts. So our solution, so writing the power series solution y of x, which contains both even and odd powers of x, as the sum of two series containing separate, respectively even powers of x and only odd powers of x, like this. Good. And using the calculated formula, nice formula for a 2k and a 2k plus 1, we have a0 times that minus 1/2 to power k over x to power 2k, this factor, over k factorial, and a 2k plus 1 are proportional to a1. a1 may be written outside the sum. It doesn't depend on the summation counter. Minus 2 or k factorial 2k plus 1 factorial minus 2 to power k x to power 2k plus 1. Okay, so we write down the two solutions in the form of a power series. Look. So this is the power series expansion of the first solution. And this is the power series expansion of the second solution. Good. And therefore, the solution is the combination of two solutions, as we expected from the general theory. Here is the general solution. General solution, a1, y2x, a1, a0, and a1 are again arbitrary. So this is what we try to find out by general theory. Okay, so combination of two solutions. So let us look at the, so as you see, we find in fact not y1x in closed explicit form, but its series expansion has been determined. We didn't find y2, but its series representation about the origin. Good? So here it is interesting to see that y1 of x, look, that one, minus 1/2 to power k x to power 2k over k factorial may be written as this. Here is x squared to power k, so in multiplying these two terms, two factors, minus 1/2 x squared or x squared over 2 to power k over k factorial. So it is interesting to see that this is nothing, to see that the first solution, y1, that is the first solution, is nothing but, do you recognize this series? Remember, what is this one? A to power k, k factorial. recall that this is nothing but e to the power a. Yes, this is the Maclaurin series of exponential function with argument a. That is kth power of exponent over k factorial. So is nothing but e to power. So look, exponent, this is exponent of our exponential function, minus 1/2 x squared. Good? Which can be in closed form. So sometimes such good surprise is the case. So surprisingly, we see that the first power series solution is very well known, as in this case. Okay, it is e to the power minus 1/2 x squared. Good. This is a function in terms of exponential function, but it is not a function that appears in the solution of a linear ODE with constant coefficients. Exponential function that may appear in the solution of a constant coefficient equation are all e to the power lambda t or lambda x, not the square of x. Okay? And y1 is this. So is it possible to write y2 in terms of an elementary function? I'm not sure. Perhaps it is no, because it is something like that. On the other hand, y2 has this form. Look, let us simplify it a little bit. X to the power 2k plus 1. So let's write one x factor outside the sum. So we have x to the power 2k here. So it remains minus 2 to the power k, x to the power 2k gives k factorial over 2k plus 1 factorial and minus 2x squared to the power k, multiplying by x from 0 to infinity. I didn't recognize this as a series expansion of a known function. Perhaps it may be a combination of some functions, or I'm not sure. So it remains second solution is written as a power series form, or is characterized in the power series form. So good. So in this case, again, we find the two solutions in the form of power series. But surprisingly, first one is expressible in terms of a nice elementary function, like e to the power minus 1/2 x squared. Good. Here is another example. Okay, here is another example. Consider the ODE again with variable coefficients, which is this one, x squared or 4 plus x squared y double prime plus 4x y prime plus 2y is 0. Good. So as you see, this is again an equation with variable coefficients. There is no general procedure to express the two solutions. And we try to find the power series representations of the two solutions. So we have to choose one point, which is an ordinary point, and expand the solution about that point. For simplicity, if 0 is an ordinary point, we prefer to obtain a power series solution about 0 for simplicity. So as you see again, or if you want, look, when you write this equation in the reduced form, y double prime plus 4x over 4 plus x squared y prime plus 2 over 4 plus x squared y equal to 0, you will see that this equation has no real singular points. Good? But if we consider the complex values of x at plus or minus 2i, when x is 2i, plus or minus 2i, the denominator of the coefficients becomes 0. So singular points are, we have two singular points, plus or minus 2i, complex. And no real singular points. Good? So x equal to 0 is an ordinary point. Good? So x0 equal to 0 is an ordinary point. So for simplicity, we prefer, of course, every real number is an ordinary point. Okay? The only singularity of the differential equation appear as a complex number at plus or minus 2i on the complex axis. Okay? So we prefer to choose x0, 0. So we propose a power series solution about x equal to 0. So first question. What is the radius convergence of the power series solution about 0? So we can answer this question without any trouble. Remember that we know that there is a non-zero radius of convergence, and it is nice to make a picture, okay, showing the singular points using x complex plane. So real x on x-axis. Okay? So complex singularities somewhere here on imaginary x. Yes, and this distance is 2 units from the origin. So we choose x0, 0 as an ordinary point. And this distance from minus 2i is the same. Minus 2i, okay, on complex axis. So distance is 2. Distance, what is important? Distance from the singular point to x0. And the two singular points have the same distance to x0. So the distance from the singular point to x0 is 2. Therefore, by theorem 2 rho is at least 2. Rho is at least 2. So it is better to write this one. Okay? So the radius of convergence is at least 2. Remember, radius is larger than the distance from x0 to the nearest singularity. Good? So this series, okay, is convergent, but we are interested in in fact, in the complex plane. It is convergent in this disk with radius 2. Good? Perhaps for in a larger region, but at least in this disk, okay, or any complex number, and the disk lying in this disk, the power series is convergent. But we are interested in the real cases, in the real x interval. So clearly here is the point 2, here is the point -2, okay? So in the interval, so y of x is sure to converge in the real x interval from -2 to 2. Good? Very nice. So all we need now is to calculate the coefficient. And the calculation of the coefficient is mechanical. Then find the series. Find the series. Okay? Or find the coefficients. An of power series solution. So to this end, we have to substitute y prime, and y double prime into the equation. So substitution of y, which is always this. If we consider x0, 0, we always look for a solution of this time, okay, for any second order ODE. Good? Its derivative is from 1 up to infinity n x to power n minus 1. Its second derivative is and y double prime n minus 1 an x to power n minus 2. You may start it from 2 because first two terms vanish upon differentiation into the ODE. We have that 4 plus x squared y double prime plus 4x y prime plus 2y then takes the form, if this is a solution. So multiply y double prime by 4. So we have this series 4n n minus 1 an x to power n minus 2 from 2 to infinity plus multiply y double prime by x squared. Would multiply y double prime by x squared. We have this n minus 1 an x to power n. This term is x squared y double prime. Good. From 2 to infinity. So x to power n minus 2, exponent rises to n on multiplying by x squared, plus 4xy prime. multiply the derivative by 4x. We have this series from 1 up to infinity, 4 n a n x to power n again, and this is x y prime. Good. Multiplied by 4. Okay. And finally, 2y. So 2 times a n x to power n from 0 to infinity must be equal to 0 if the proposed power series is indeed a solution satisfying the equation. Now we have to collect the terms. Now it seems that the last 3 coefficients, power series, may be collected under one sigma sign. No problem in writing this. This one, we can write it, we can take the lower limit as 0 without any trouble. Okay? Because we add the 2 terms. And when corresponding to n equal to 0 and n equal to 1, both 0. So adding 2 zeros to the sum doesn't change the value. And here we can start this series from 0 without any trouble, because when we started from 0, we add the term at 0, which is 0. And this so that this series, the 3 series, may be written immediately under one series. So n minus 1 a n, good, plus 4n a n plus 2 a n, or even a n is a common factor, plus 4n plus 2 a n x to power n. Okay? And to write this again, we need a shifting to make the series proportional to x to power n, okay, or containing, to make the series a series containing x to power n instead of x to power n minus 2. In place of n, we are going to put n plus 2. Therefore, this will be, the lower limit will start from 0. And here is 4, n plus 1, n plus 2, a n plus 2, x to power n. Must be equal to 0. So the 2 series are similar. Good. So we can write them under one sigma sign. So we have, now we have, let's write it in another blackboard. So we have this one, 4 n plus 1, n plus 2, a n plus 2 plus n minus 1 plus 4n. So let's write them an n squared minus n plus, so plus 3n plus 2 an, all proportional to x to power n, must be 0. So this is the left-hand side of our ODE. This is 4 minus x squared y double prime plus 2xy prime plus 4xy prime plus 2y. Okay? I mean the left-hand side of the ODE. Good. We get that, implying the recursion, which recursion, and interesting to see that this is n plus 1, n plus 2 times a n. Therefore, our recursion becomes 4 n plus 1, n plus 2, a n plus 2 plus n plus 1, n plus 2, a n, which must be 0. So this term cancel each other out. Okay? So equating the coefficient of x to the power n to 0, we get the so-called recurrence equation, which seems that it is of the form a n plus 2 is minus a n over 4 for n, 0, 1, 2, and so on. So very nice recursion is obtained. This is the recurrence equation or recursion relations to determine for a n. So let's solve this recursion again, term by term. Solving the recursion again for n equal to 0. What you get? A2 is minus a0 over 4. Okay? For n equal to 1, what we get? Minus a1. A3 is minus a1 over 4. Good. For n equal to 2, we have a4 minus a2 over 4. So minus 1 squared over 4 squared, a0. Very nice. For n equal to 3, a5 is minus a3 over 4. But a3 is known, so minus 1 squared over 4 squared a1. So obviously, we see that a2k is written in terms of a0 of the form minus 1 over 4 k a0. Good. And similarly, the coefficients with an odd index is written, all are written in terms of a1 in that form. Minus 1 to the power k over, or minus 1 over 4 to the power k a1. So the coefficients have the same structure, but the one proportional to, or which are the coefficients of an even power of x, are proportional to a0, and the terms proportional to odd powers of x are written in terms of a1. Okay? So again, we split the series into two parts and use that result for the coefficients. So the general solution y of x, again splitting the series into two parts containing even powers of x and odd powers of x separately. So a 2k is minus 1 over 4k a0 Good. So we have a0 minus 1 over 4 to power k x to power 2k from 0 to infinity. And a 2k plus 1 is minus 1 over 4 k times a1. Okay? So let's write a1 outside. Minus 1 over 4 k x to power 2k plus 1 from 0 to infinity. Good. And better is that x to power 2k, let's incorporate this. So x squared to power k. So we have minus x squared over 4 to power k. And x to power 2k plus 1. So one x factor may be written outside. So we have a1x from 0 to infinity. So we have x to power 2k multiplying by minus 1/4 to power k. So minus x squared over 4 to power k. Good. This is the solution. So again, we have y1. This is y1, the series expansion of the first solution. And this is together with this x. This is y2 of x, which is the series expansion of the second solution. Good. And do you recognize this? That's geometric series. So if we recall the geometric series. What is it? Say z to power k from 0 to infinity. Converge to what? 1 over 1 minus z for z smaller than 1. Okay? So this is the geometric series with z minus x squared over 4. So it is convergent for what? Geometric series convergent for absolute what does it mean? And what does it mean? X squared is smaller than 4. X is between minus 2 and 2, supporting our estimation in the first part. We already know that the radius of convergence must be at least 2. Okay? And that is the case. And similar is true for this one. And again, look, the two solutions are written in terms of elementary functions. Here is the k, here is the result. Two solutions are written now. Two solutions, y1 and y2, are both expressible in terms of elementary functions using the geometric series, okay? That is minus x squared over 4 to power k from 0 to infinity is nothing but 1 over 1 minus x squared over 4. Good. Multiplying throughout by 4, we have 4 over 1 plus x squared. And therefore, hence, y1 of x is nothing but 4 over 1 plus x squared, and y2 of x is x times 4 over 1 plus x squared, or 4 plus, sorry, multiplying throughout by 4. Good. We have 4 over 4 plus x squared. So, and this y of x is a0 y1 a1 x 4 over 4 plus x squared, or c1 over 4 plus x squared, c2 times x over 4 plus x squared. Good. So I choose 4a0 as c1 and 4a1 as c2. So again, we write the two solutions in terms of elementary functions. Now, what about the validity of these two solutions? If you write the solution as in terms of power series like this, a0 minus x squared over 4 to power k plus a1x minus x squared over 4 to power k. Good? These are similar. If you write this as a power series, we know that these are convergent for that. So for x between minus 2 and 2. Okay? But when you write this series, we take the sum of the series. Now looking at these two solutions, they are valid everywhere. Good? And actually, from the differential equation, since there is no singular point for at a real point, okay? If you recall the basic existence uniqueness theorem, there is no singular real point. So we expect that the two solutions are valid throughout R. Yes? I'm not saying talking about the theorem about the series, power series solutions. I'm talking about the general solution, general theory of linear differential equations, where we are looking for an interval in which the coefficients are all continuous. So look, 1 over 4 plus x squared, or if you look at the differential equation, what is the differential equation? This one, 4 plus x squared y double prime plus 4x y prime plus 2, was it that? Yes? So even when you consider the reduced form, look, the coefficients are defined for all x. Therefore, unique existence theorem or general theory of linear differential equation tells us that there exists a solution valid for all x. Good? So that is that this solution actually is valid for all x. But if you express the solution for a moment, if you think that you do not you are not familiar to geometric series and its sum, and leaving the two solutions as power series, okay? These power series representations of the two solutions are valid for all x between -2 and 2, which is a sub-interval of this interval. Yes, this is an important point. Okay? Okay, as a final example, find power series solutions of the equation 2 plus x y double prime. Look again, the equation is very simple looking one. The coefficients are polynomials, and even they are linear polynomials. The coefficient of y double prime is 2 plus x. Coefficient of y prime is x. Minus y is 0. Okay? So again, x equal to 0 is an ordinary point, isn't it? Or it is better to write the equation in that form, 2 plus x y prime if you want. 1 over 2 plus x y equal to 0. So writing this form makes the singular point more obvious. Okay? So x equal to -2 is a singular point. Good. Where the coefficient of y prime and y, okay, at least one coefficient is undefined, is enough to say that at some x is enough to say that there is a singularity at that x. Okay? So when x is -2, there is a real singular point. And this is the only singular point. Only singularity of the ODE is at x equal to -2. Good. So other points are all ordinary points. So choose again. Choose for simplicity x0 equal to 0, which is an ordinary point. Ordinary point. So accordingly, we propose a power series solution of the form x to power n again. So the radius of convergence is very well known that it is non-zero. What about rho? At least 2. Good. So the distance, as you see, choosing x0 equal to 0 on real x-axis, there is only one singularity at -2. So the distance from x0 to -2 is 2. This is the distance. So rho is at least 2. So it must be larger than or equal to 2. Okay? It is at least d. So this power series is sure to converge, which is guaranteed to converge in this interval. Okay? In this open interval. Now, theoretically, we know everything. There is a solution. So to make this solution explicit, we have to find the coefficients. And this can be made by substituting into the differential equation. Okay, so similarly, substitution of y an x to power n. Its derivative, which is an x to power n minus 1 from 1 up to infinity. And second derivative, which is n minus 1 an x to power n minus 2. So you will see that these are all the same. If you choose, of course, x0, 0. Okay? So we are looking for a solution of the similar form for any differential equation. Substitution of this into the ODE. I mean this one. 2 plus x y double prime minus x y prime minus y. Now multiplying the second derivative by 2, we have this series 2n n minus 1 an x to power n minus 2 from 2 to infinity plus x times y double prime. So we have n minus 1 an multiply y double prime by x. So we have x to power n minus 1. Okay, from 2 to infinity. Then minus x times y prime. Multiply y prime by minus x. So we have minus n an x to power n. Good. Multiply x minus n x to power n minus 1 by x. So we get this from 1 to infinity. And finally minus y. So minus an x to power n from 0 to infinity must be 0. Good. So we have to collect the 4 series. Okay. Writing a single series. So the last 2 may be written under 1 sigma sign immediately again. So write 0. So the 2 series start from 0 up to infinity. They are both related to x to power n, okay? Or written in terms of x to power n. And starting from 0 doesn't cause any problem because we add 0, which doesn't change the actual value of the sum. So the 2 series is with a minus sign, n plus 1 an x to power n from 0 to infinity. And to write this series in terms of x to power n, I shift n to n plus 1. Therefore, the series will start from 1 up to infinity, n times n plus 1, an plus 1, x to power n. Okay? And to write this series, I shift n to n plus 2. Therefore, the series will be started from 0 with the shifted index to n plus 1. N minus 1 becomes n plus 1. N is shifted to n plus 2. An plus 2 x to power n. Okay? Must be equal to 0. So again, this term may be started from 0 without any trouble. At 0, we add 0, no problem. And therefore, all the 3 series may be written under 1 sigma sign. So from 0 up to infinity, 2n plus 1, n plus 2, an plus 2, plus n plus 1, an plus 1, minus n plus 1 an all multiplied by xn must be 0. Okay? To satisfy the differential equation. So this implies the recursion relation. So n plus 1, n plus 1, n plus 1 cancel each other out, implying this relation. 2n plus 2 a n plus 2 plus n a n plus 1 minus a n must be 0. So we get a 3-term recursion now, okay, containing a n plus 1, a n plus 2. In the previous examples, remember that the recurrence relation is such that a n plus 2 is written directly in terms of a n. Now, this is the recurrence relation. So the recursion we obtain is so do not forget, we expand the solution about 0, and the power series about 0 has at least the radius of convergence, which is 2. At least 2 is the radius of convergence. Now the recursion relation for this is a n plus 2 is minus n over 2 n plus 2 a n minus 1 plus a n over 2 n plus 2. Oh, that's right. 1 over this a n. Correct? This is minus plus n plus 1, and this is a n. Okay. For n 0, 1, 2, and so on. Okay, so starting from 0 to solve this recursion, we have a2. When 0, we have 1 over 4, a0. Good. So a2 is written in terms of is there any mistake? Let's look at my notes. Okay. So I have a mistake in my notes. Okay, so let's solve this recursion. A2 is 1 over 4 when n is 0, a0. So for n equal to 1, so a3 is minus 1 over 6, correct? A2 plus 1 over 6 a1. Good. So a2 is written in terms of a0, but a3 is written in terms of a2 and a1, but a2 is written in terms of a0, so we have minus 1 over a2 may be written as 1 over 24 a0 plus 1 over 6 a1. So a3 is expressible in terms of both a0 and a1. In the previous examples, recall that even index terms are all expressible in terms of a0, and odd index terms are all expressible in terms of a1. But in this example, this is not the case, a little bit more complicated. Not complicated, but it gives a result which is more complicated than the previous examples. So when n is 2, we have A4, which is minus 2 over 8. Okay, 2 times 4. So A3. Good. And plus 1 over 6. Or 1 over 8, sorry. 2 plus 2, 4 times 2, 8. A2. Now, A3 is written in terms of A0 and A1. A2 is written in terms of A0. Therefore, we have minus 1 over 4 A3, which is minus 1 over 24 A0 plus 1 over 6 A1 plus 1 over 8 A2. And A2 is 1 over 4 A0. So this, good. And now let us write this simplified, collecting the terms proportional to A0 and A1 separately. So we have 1 over 4 times 24 plus 1 over 4 times 8 A0 and minus 1 over 4 times 6 A1. Good. So one more term. A5. So no obvious formula for the general term. A5 is written, let's like A5 when n is 3. So minus 3 over 2 times 6. Okay? No, 3 times 5. So we have 3 over 10, correct? 2 times 5 times A4 plus 1 over 10 A3. But A4 and A3 are both expressible in terms of A0 and A1. Let's write them. Minus 3 over 10 A4, which is that one. 1 over 4 times 24 plus 1 over 4 times 8 A0. And minus 3 over 10 times this, and so minus minus plus, so 4 times 6 A1. Good. What else? 1 over 10 times A3, and A3 is minus 1 over 24 A0 plus 1 over 6 A1. Good. Now, there is no obvious formula to express the general term an or a2k or a2k plus 1. So let's write. So it seems that A0 remains arbitrary. A1 remains arbitrary. But A2 is 1 over 4 A0. A3 is minus 1 over 24 A0 plus 1 over 6 A1. A4 is what we find 1 over 4 times 24 plus 1 over 4 times 8 A0 minus 1 over 4 times 6 A1. And A5 seems to be, let us collect the terms proportional to A0 and A1. With a minus sign. 3 over 40 times 24, good, plus 3 over 40 times 8, and plus 1 over 10 times, or 240 A0. No, I write this term. So 3 over that. Okay, so I collect these two terms and this term. So as you see, it is very difficult to calculate the coefficients. So the terms proportionals to A1 are 3 over 40 times 6. So that's right, 24 plus 1 over 60 A1, I guess. Good. So, and it seems that it is difficult to give a formula. So we write the first few terms of the power series solution explicitly. In that case, that is, y of x is this one, a n x to the power n. So a0 plus a1x plus a2x squared, a3x cubed, a4x4, a5x5 plus dot dot dot. Okay, and actually we have a0 plus a1x. So every coefficients are written in terms of a0 and a1. So a0 and a1 remain arbitrary again, which are expected because the solution should contain only two arbitrary constants. I'm talking about the general solution. A2 is written as 1 over 4 x squared. Okay, 1 over 4 a0 x squared. Good. A3 is written as plus minus 1 over 24 a0 plus 1 over 6 a1 x cubed. This is a3. And a4 is the number here. Which number? Multiply this by 3, 24. So is it 4 over 4 times 20? Is it 96? And simplifying, 2 over 48, 1 over 24. So 3 plus 4 over 24 is 1 over 6. I guess this is 1/6. Is it true? Maybe 1/6 A0 minus 1/24 A. Okay, so this coefficient here seems to be 1/24. Okay, so 1/24 A0 minus 1/24 A1 x4, and finally let's write this coefficient. Perhaps, okay, that's all. Unnecessary to write the last coefficient. So, but the solution is in the form. I didn't write the term proportional to A5. So I obtain the first few terms. So there are terms proportional to A0, which are 1/4 x squared, this term, minus 1/24 x cubed, this term, plus 1/24 x4, this term, plus dot, continuing in this way. And there are terms proportional to A1. They are x, this one, and plus 1/6 x cubed, and minus 1/24 x4, plus dot. So this is the series expansion of the first solution. We write explicitly only the 4 term, and this is the series expansion of the second solution. The first 3 terms are written explicitly. Okay, so again, the general solution is the combination of 2 functions whose series expansions are given, and A0 and A1 are the 2 arbitrary coefficients appearing in the solution. So from this example, we understand that to calculate the general term AN in a proposed power series solution explicitly, the general term, let's say, in terms of explicitly in terms of a simple formula is not possible. In general, as is shown from this example. Good?